Welcome to today's webinar, Harnessing the Power of CFD for Marine Engineering, brought to you by Convergent Science. Thank you for joining us today for this new installment of our webinar series. My name is Mathias and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and witness how CONVERGE CFD software can be used to model oceanic wind wave field generation, ship hulls, ship propellers, and floating offshore wind turbines. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flow in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast and accurate results for our clients. Now it is time to introduce our two speakers for today's event, Mathias Vangoe and Xiao. Mathias is a principal engineer on the Convergent Science application teams. Mathias received his PhD at Johannes Kepler Universities, where he studied multi-phase modeling for blast furnace application. Mathias has been with Convergent Science for nearly 4 years. Xiao is a senior research engineer on the Convergent Science application team. Xiao received his PhD at the University of Connecticut, where he studied operability and emission of gas turbine combustion. Xiao has been with Convergent Science for 3.5 years. During today's webinar, if you have a question for my colleague Mathias and Xiao or the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to Mathias. Thank you all.
Thank you, Mathias, for the kind introduction. As Mathias said, my name is Mathias, and I will give you the talk of the first part of today's webinar of using CONVERGE for marine applications. So what I want to share with you today is I want to give you some insight in our ongoing work and validation work related to ship CFD modeling. So the topics I will try to cover today is mainly related to propeller, where we'll look at some open water simulations, some detailed transient comparisons, as well as cavitation modeling. And we will also look at some hull resistance modeling, where we're interested in the wave pattern, as well as the drag resistance for both fixed sink and trim, as well as dynamic sink and trim. But before that, just a few words about why we're doing all of this. So shipping is very important for global trade, and even though it's a very efficient method of conducting this transportation, it's still responsible for a large amount of greenhouse gas emissions. So if we're looking at the graph here on the right-hand side, we see a division of the global CO2 emissions by transportation sector. So we see the two largest contributors are light and heavy duty sectors, but the third largest one is the shipping. So in global, or let's say absolute numbers, we're talking close to a gigaton of global CO2 emissions annually. So with the current environmental situation, of course, we need to reduce emissions to, let's say, achieve those milestones. And to achieve those goals in the shipping sector, we must look at alternative fuels or propulsion systems, as well as continue to improve the overall ship efficiency. So CONVERGE is a well-established tool to aid the design of marine ICs, also for alternative fuels, and the multi-physics capabilities are powerful for also studying other parts of the ship design, which we will focus on in this talk. So let's jump right into it with starting with propeller modeling. So getting first on with the open water modeling. So for all validation cases related to propeller, we are using the the data by the Potsdam propeller test case by SVA Potsdam. So this particular one is the controllable pitch propeller VP1304. And for the open water test, we use this configuration as illustrated here on the bottom left corner. So the tests we are modeling are all used at a constant rotational speed of 15 rotations per second. And in those tests, the thrust and torque were measured on the blades. So really the objectives of these simulations is to establish this open water characteristic curve, where we are looking at the dimensionless thrust, torque, and propeller efficiency for a wide range of advanced coefficients. So generally speaking, those coefficients are made non-dimensionless by just looking at the torque and the thrust on the blades, and made dimensionless with the propeller diameter and the rotation rate and density. What I just want to highlight a little bit more is when we're talking about advanced coefficients, is basically a non-dimensional form of the normalized vessel advanced velocity. So how we have set this up in Converge, on the right side we see the computational domain. So we have the propeller here located in the middle in this backwards facing configuration, enclosed in a large domain. So this is a large cylindrical domain to simulate these open water conditions. So it's surrounded by symmetry boundaries. And we have the inflow coming from this purple boundary here with inflow velocity depending on which advanced coefficient we're looking at, and with the normal pressure outflow on the other side. So these particular simulations, we're interested in the steady state phenomena. So we are using a multiple reference frame or MRF approach. So we are not rotating the propeller. And we use a k-omega SST model. And depending on the operating conditions here, we are around, let's say, 1.5, 1.6 million cells, depending on the AMR. So we use adaptive mesh refinement here based on velocity as well as the Y plus. So the reasoning why we're using it for the Y plus in these cases is that we kind of want to have as uniform Y plus over the entire blades as possible, as well as we want to use the same simulation setup over the full range of advanced coefficients. So looking at some results, some snapshots from one of the cases. On the top side, we see the pressure distribution on the pressure side as well as on the suction side. So here we see the large pressure gradients on the leading edge on both sides. And we see that there's low pressure zones are located on the leading edge as well as here at the blade root very close to the hub. So if there would be anywhere we would expect some higher cavitation risks, we would see this here. But what is more interesting maybe is if we look at this Y plus distribution on the propeller, we can see how the Y plus is increasing, of course, towards the edges or the tips of the blades because the velocity is increasing. And we can see how the AMR has kicked in towards the blade tips to refine there to keep the Y plus in a let's say reasonable range. So we are relying on wall functions here. We are not fully resolving the blades, and the reason for this is that our intentions is towards to go to ship scale where it might not be fully reasonable to fully resolve the boundary layers at those length scales. So looking a bit more quantitatively for the open water case, we see here the open water curve. So we have the thrust coefficient with the square symbols, and the torque coefficient with the circle, and the efficiency with the triangles. And the red curves are the simulation results, and the black ones is the measured ones. And we can see overall throughout the entire range of advanced ratios, we managed to very nicely capture the thrust and the torque with, let's say, the error in around the maximum error of around 5% or so. And we also managed to nicely capture the peak efficiency point at 1.4 advanced ratio coefficient. So moving on to the transient simulations. So here again we're using the case and data from the PPTC. So this particular test we're using the same propeller, but instead of the open water configuration, these measurements were done in a cavitation tunnel with a fixed dimension of, or a cross section of 600 times 600 millimeters. And in these cases, their LDV measurements were performed to give a very detailed description of the transient velocity field. So what we have is we have several planes downstream and upstream of the propeller with many monitor points where the velocity has been measured in all the different components. So this particular case has an advance ratio of 1.25 advanced coefficient and a rotation speed of 23 rotations per second. And what we have done is we have run this simulation and compare the result at two different planes, which are highlighted in red color here. At 0.1 times the propeller diameter downstream and 0.2. And on these two planes, we have two monitor points on each plane, located as shown here on the bottom right, where we have 1 point at 0.7 times the propeller radius and one at the very edge towards the blade tip at 1 of the radius. So the simulation setup is again very similar, but instead we don't have this backward facing configuration anymore. It's the forward facing shaft, and we don't have the open water geometry anymore. We have actually modeled the actual geometry of the cavitation tunnel. So we have this cross section as described before with some rounded corners. And again, we have the inflow from the left side and the outflow from the right side. The main difference is that these cases are no longer steady state. We are running this one in transient configuration, so we are actually rotating the propeller with the moving boundary approach in Converge. So we use the k-omega SST turbulence model also here, but the cells, we allow a bit more refinement using a AMR in this case, so the cell size tends to go up towards 9 million towards the end of this simulation. Since we're not looking directly at forces, we don't have AMR enabled on the boundaries itself, but only based on velocity and also helicity to try to preserve the vortices as good as possible. So looking at one of these simulations, we have here on the left side an animation showing we can see the cut plane through the propeller, showing how the mesh is updating over time. We have also another cut plane showing the velocity magnitude, and here the vorticity is illustrated by the isosurface of the Q criterion. So maybe more interesting is when we look on the animation on the right-hand side, again showing the same quantities, but we can see how the AMR is working to not only refine based on velocity, but we can see that this finest level of refinement is following the tip vortices as they're being transported downstream. We manage very nicely to capture this phenomenon. But again, looking a bit more quantitatively, so here we have the velocity, different velocity components comparison between simulation and experiment. So we have the simulation results in the solid lines, and the red color showing the axial velocity, blue showing the tangential component, and green the radial component, and those ones are all normalized based on the advanced velocity. So on the left-hand side, we've seen the monitor point at x over d, so the 0.1 plane closest to the propeller at the 0.7 times the propeller radius location, and on the right-hand side at the r over r 1.0. So these results are the transient velocity components over 1 revolution of the propeller, so 360 degrees. So this means that we have all the 5 blade passings captured in this monitor. So we can see overall we manage very well to capture the magnitude and the trends of this transient phenomena. With some, we can see we do not fully manage to capture the magnitudes at the very edge of the blade tips, where as the blades are passing by. So in these regions, the gradients are very strong, and it's possible we could have improved this by refining the mesh, but we have not done this at this point. Because we can see as we move, so here are again the same measurements, but for the plane further downstream, you can see already moving down only a little bit that these very strong velocity gradients at the blade tips have diminished a little bit, and we can see now we manage much better to also capture the magnitudes. So moving on to cavitation modeling. So we have again run one of the operating conditions also given in this PPTC report, and it's this 2.3.1 condition. So we have our advanced coefficient of about 1 and a cavitation number about 2, and we now have a bit faster, so it's 25 revolutions per second. So this simulation uses the exact same setup as the transient one previously showed, but the main difference is we are not running single phase anymore, as we need to also model the vapor. So it's a multi-phase simulation using the volume of fluid approach. And here we're using a Xiao cavitation model. And if you're familiar with CONVERGE, this cavitation model is not currently in the software, so we implemented a few new ones which will be available in our upcoming release. So here we are using the Xiao model, and it's no longer the K omega SST turbulence model. Now we are using the RNG K-epsilon. And just looking at some of the results of the cavitation. So on the left-hand side, we see the isocontour of the volume fraction of vapor of the 0.5. And we can, so on the left-hand side, we have the simulation results for one blade. On the right-hand side, we have the sketch from the report of the location of cavitation observed. And we can see that we managed very nicely to capture this location as was reported. But not only the location, we also managed to reasonably capture the reduction in thrust due to cavitation. So we observed a 3.1% reduction of thrust, whereas in the report it was measured to 3.75%. So that was all what I wanted to show quickly about propellers. So moving on to the hull resistance simulations. So to do this validation, we ran simulations on this INSEAD 2340 model of this US Navy naval combatant. And here we are using the measurements and data reported by Olivieri et al. In this paper. And in these tests, they did many measurements of this scaled model in this water tunnel. And here we have much data related to, we have all the wave elevation profiles, we have the drag decomposed in pressure and viscous components, and also the dynamic trim and sinkage, which are occurring for a wide range of fluid numbers between 0.05 and 0.41. So we have this data for a wide range of vessel speeds. So we can see here's a table of some of the model parameters. So I just want to point out that this particular case has a scaling factor of 24.8, so almost 25. So how we set this up in CONVERGE is here again showing on the right hand side. We have a side view of the computational domain. So we have the boat located at this location with about 1.5 times the boat length of distance upstream to the inflow boundary, and about 3 times the boat length downstream to the outflow boundary. And here we are, as we are interested in the wave elevation profiles, we are modeling this free surface at this origin location, so it's set equal to 0. And to do this, we are again using the volume of fluid approach. So as in these cases, it's great importance to capture these waves with as great accuracy and resolution as possible. So we are using a front capture model, which is HRIC, which also enables some surface compression to try to keep this as resolved as possible. Again, it's the K epsilon turbulence model. And as we are very interested in forces, even at this scaled model, the length scales are quite large. So we are using, we are modeling the boundary layer using the inlaid mesh feature in Converge. And so we have a first boundary layer cell size of about 1 millimeter with 5 layers at 1.5 expansion ratio. So I want to highlight the goal here is not to fully resolve the boundary layer all the way down to y+1 or so. We are still targeting y+ of around 30. And in case of the free sink and trim simulations, basically it means that in those simulations the boat is allowed to float freely and also pivot in 1 degree of freedom around its center of mass. So it's a 2 degree of freedom fluid structure interaction used to model the free sink and trim. And in these cases, we have, as reported in the paper, we use a model density of 90 kilograms per cubic meter. So looking at some of the results, so here is showing for one case, so this particular one is at fluid number 0.28. And what we see on the right side is the iso surface of the waves. So it's the iso surface of alpha 0.5 colored by the normalized wave elevation height. And what we have done is we have taken these 3 cut planes as highlighted by the dashed black lines and plotted them and compared them against the wave elevation height against the measurements. And we can see, especially close to the boat, we managed to very nicely capture the different wave features going all the way downstream as the measurements are reporting. And this trend continues when we go a little bit further away from the boat. What we can see is that the plane furthest away, we see that those waves do not fully dampen out as we would expect from the measured values, so which would maybe need a little bit more of investigation. But overall, is what we want to compare is the forces. So this was the forces result for the fixed sink and trim simulation. So what we have is on this plot on the left, we have the pressure component of the drag force, and on the right, the viscous components. And those ones are reported for 3 different speeds. So we had the fluid number 0.1 in the red, and 0.28 in the blue, and the 0.41 in the green. And again, the simulation results are visualized with the solid lines and the experimental one with the dashed lines. So what we can see is both for the pressures and the viscous force that we manage quite well to match what was reported by the experiment, with some exception maybe for the pressure force and the viscous force at the highest fluid number case, where the pressure force is slightly underpredicted and the viscous force a bit overpredicted. So looking again at the free sink and trim, so said here the boat was allowed to float and rotate or pivot around its central mass freely based on the flow conditions. And on the right side, we see again the pressure force reported and the viscous force. And here they are also compared between its fixed component, so the results reported in the previous slides and the updated ones with the free sink and trim. And we can see generally we don't see too much difference in the forces, except that it actually seems to improve the pressure force prediction for the highest speed case. And also looking at the graph on the left side, we compare the dynamic sinkage observed as we go between the different speeds. So we have at the lowest velocity at fluid number 0.1, there is not the boat is pretty much staying in its initial position, but as we keep increasing the speed, we see that the boat starts sinking lower into the water, as also reported by these measured values. So this was very quickly. I've showed you some of our current and ongoing validation work for the propeller, using the Potsdam propeller test case for some steady state, steady open water conditions, and also some detailed comparisons of the velocity field for transient simulations. And we also did some investigation of some newly implemented cavitation model for this PPTC test case. Also showed you some validation work we're doing for the hull resistance and wave pattern prediction on this INSEAD 2340 model for both fixed sink and trim and also the dynamic prediction. So some things we are wanting to do and working on is so this is still, let's say, quite basic, and we're starting from the simpler simulations, and what we intend to do is continue to some more advanced simulations such as self-propulsion, maneuvering, and underwater noise model. And also, once we have only showed so far results on model scale, the intention is also to perform similar validation going to full-scale ship scale. So I want to thank you for your attention of this first part of the webinar. And now I will hand over the ball to my colleague, Xiao. Thank you.
Okay, thanks, Mathias. Hi, everyone. I'm Sharon from Convergent Science. After Mathias talked about the validation cases for propeller and boat hull, now I will present a few cases for boats and floating offshore wind turbines with a focus on motion simulation in more realistic scenarios using CONVERGE CFD. In the following slides, I will demonstrate how to use CONVERGE for boat simulation at fixed boat speed, simulation of wave impact on boat driving, simulation of boat driving on open water, and floating offshore wind turbine simulation. Additionally, I will introduce some advanced features about simulation cost control of marine applications. First, let's take a look at this very common scenario that a boat drives at a fixed speed. The boat's pitch and drag force at a certain running speed are very important parameters to evaluate the boat designs. However, these parameters are difficult to predict due to complex relationships between the boat pitch, position, and drag force and other variables. Usually, the boat speed and the relative angle between the boat hull and the thrust direction are known from the design aspects, but the thrust magnitude, drag, boat balance position, including the pitch and the vertical position, is hard to simulate since they are coupled with each other. For example, if the boat is at a higher position, the lift probably not enough to balance the boat, then the boat will lower its position. At the same time, the drag force will change. Also, the boat could rotate. So a dynamic motion simulation is necessary to predict the drag and balance position for the boat simulation at a fixed boat speed. To solve this complex problem, we designed this active thrust adjustment scheme, which allows for pitch and drag prediction for the running boat scenario. As the animation on the left-hand side shows, the water comes at a fixed speed, and we will release the boat from the beginning. At each step, the active thrust adjustment scheme will adjust the thrust magnitude to balance the drag. And to maintain the same relative angle between the thrust and the boat hull, we will also rotate the boat the same degrees as the boat. We will also rotate the thrust direction the same degrees as the boat rotates. Meanwhile, the boat is allowed to move vertically to find its vertical balance position. So after sufficient iterations, the boat will achieve its balanced location as shown on the left-hand side. After 5 seconds, this example case achieves its balanced position. In this way, the drag and the pitch can be found for the boat running at a fixed speed. So in real life, the water is not always as steady as calm water, and the waves are usually very common in the lakes and the ocean. So here I will demonstrate how to use CONVERGE CFD to simulate the wave impacts on boat driving. In CONVERGE CFD, we have a package for the wave generation, including 2D, 3D, regular, irregular, linear, or nonlinear waves. And for more information, please check our YouTube channel, CONVERGE CFD, and watch our previous webinar, how simulating wind turbines can accelerate the renewable energy transformation. Now let's take a look how to use CONVERGE CFD to simulate the wave impacts on the boat driving. For the first stage, the boat can achieve its balanced state with drag balanced by the thrust using the advanced thrust auto active thrust adjustment scheme I mentioned previously, and then the waves will be introduced from upstream. Once the wave approaches the boat, the thrust magnitude will be locked, and the balance state will break. So from the cases we tested on the right side, the higher wave will cause the boat to rotate greater, so it could be a safety concern. And CONVERGE CFD has the capability to use the user-defined functions (UDFs) to simulate the FSI object. So the flexibility of UDFs in CONVERGE can allow the users for various options in running the boat on open water. The external force on FSI objects can be fixed or variable. Like shown on the left-hand side, the thrust direction can be changed during the simulation, so we can mimic the turning process in the boat riding. And on the right-hand side, we keep the thrust direction fixed, and the boat acceleration process can be simulated. Besides the motion simulation for the boats, we also have very successful experiences in floating offshore wind turbine simulations. CONVERGE CFD has a fully coupled CFD package with a multitude of options for rotor modeling. Also, it's coupled with various multi-physics models for realistic simulations. And we have a lot of validated cases in the areas of floating offshore wind turbine simulations, like OC4 and OC6 projects. Please reach out to us for more information. And after talking about different scenarios in simulating the motions of boats and floating offshore wind turbines, here I want to talk about the simulation cost reduction of marine applications. So it's very common that marine application has a large simulation domain and complex motions. It could be very expensive to do the simulation. And here I will introduce a couple of advanced features to reduce the simulation cost of marine applications. The first feature is called FSI object updated at intervals. So instead of updating the FSI object at each time step, which could be expensive, CONVERGE CFD can allow the user to update the FSI object at intervals, which can reduce the cost. So we take advantage of the different time scales between the FSI object motion and also the turbulence. So we can use this FSI object updated at interval feature for the marine application. Our second feature is called moving, embedding, and AMR regions. Since we have a large simulation domain and at the same time the local embeddings around the FSI object are necessary for sufficient grid resolution, then we have this moving, embedding, and AMR regions to move with FSI object which will reduce the total cell count in the simulation. And here I want to briefly mention why the users should use CONVERGE for marine application simulations. First, we have very convenient grid control techniques. The fully automated meshing process of the Cavitation grid will eliminate user meshing time, even for very complex geometries. We have different grid control techniques for the Cavitation grid, like fixed embedding and adaptive mesh refinement, AMR. Also, the inlet meshing is available for stationary or moving structures. And secondly, there are many high-fidelity physical models available in CONVERGE CFD, including turbulence, VOF, and FSI. Also, CONVERGE has been validated for a variety of marine applications, like oceanic wave generation, ship hulls, ship propellers, and floating offshore wind turbines.
Thank you all for joining today's webinar and for all your questions. Please use the QR codes in this slide to reach out to us. You can use the contact us page, and you can sign up for our newsletter. If you'd like to have more information about CONVERGE, visit our website, convergecfd.com. You can create an account and access our free on-demand training videos, including volume of fluid modeling and fluid structure interaction modeling. Finally, I would like to invite you all to our 2023 CONVERGE CFD conference from the 26th to the 28th of September. Listen to prominent speakers in industry, academia, and government as they talk about our latest CFD trends and best practice for efficient simulation. Presentation will focus on these four industries: automotive, aerospace, energy, and biomedical. Mr. Ben Hodgkinson, Technical Director of the Red Bull Ford Powertrain, will be our keynote speaker. Red Bull Ford Powertrain was created to develop a new racing power unit that runs on sustainable fuel for Red Bull's F1 team. Don't miss Mr. Hodgkinson's keynote address on how CFD can help win races. All are welcome at this free event held online. Thank you for your time and have a great rest of your day.